Hello, and welcome back to another Engineering Wizard YouTube video. First off, we're going to start by writing the Ohms Law equation, going over some intuition behind it, writing out its three different forms, because we're just going to be using the first three variable form of it, not the four. So we're going to cover the four later and add it into our list, but today we're just going to go over the three variable form, which is V equals IR. So let's get that written down. So here's our simple equation, multiply sign there. V equals IR. It's probably one of the most fundamental equations, and you need to memorize that. That's it. I couldn't tell you how many times I've written that on a test for different classes, even if it was just just to think through a problem. Very, very helpful. So let's write the other two forms of it first to start off with solving each one of the variables. Okay, perfect. So this is each one of them solved for their own value, and they describe how you can solve for any of these V, I, or R. So first off, let's start with voltage. Voltage is, all it is a potential difference. So we can't have voltage at a single point. Doesn't really work like that. But we can have voltage between 2 points. That it kind of have to have 2 points to have a difference between them. We can't have a difference at a single point. It doesn't really work like that. Another way you could explain voltage is by a difference in height. This is a little bit more rough, but for understanding, we'll start with this. Let's say we have a measured reference node at the ground, and we're standing up on top of a building. We do have a height difference here. And this height difference can be akin, how you think of it, to our voltage, say, delta. So this delta would be our difference between these 2 points, and therefore our difference in voltage. In this case, a difference in height, but difference in voltage. Another interesting fact about voltages, it doesn't have to have flow to work. So we don't have to have a flow for our voltage to exist. This is perfectly valid to say there's voltage between these 2 points. We don't have, like, let's say 10 volts. 10 volts. So we don't have to have any connection here to have a difference in voltage, unlike current or effectively resistance either. So to have a difference in voltage, we can just have it open. That's fine. So no flow, no like flow of electrons or anything needs to exist to have a difference in voltage. Next, current. Current is defined as the flow of electrons through a certain space in a certain time. And that exact number is roughly, I believe, 6.241 quadrillion electrons flowing through a certain area per second. Humongous number. And in order to have current, we must have flow. So this would indicate that there's a circuit pushing these through to flow. And without that, we don't have anything. So in this example here again, we have no current. Because we have no closed circuit for it to flow, no closed path, we have no current. Only when we add a bridge for these to flow through, we do have current. And in most examples, it's given as a resistance. But not super important yet. That's just some of the basic properties of current. So next, keep this. Next is resistance. Resistance is kind of an intrinsic property of a lot of materials, and resistance is what it sounds like. It's a resistance of flow. So electrons flowing through a tube are not going to be flowing perfectly. They're actually going to hit things, and they're going to bounce around, and they're going to do all sorts of things. So it's going to hit, bounce, 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 all that stuff. And that bounce and that like impedance of movement, the restriction of flow for the electrons is the resistance. For a lot of materials like metals, copper specifically, and a few others, the resistance values are relatively very low compared to a lot of other materials. So there's not many of these impeding objects in a like copper wire. There's some, but not many. In superconductors, there's zero. Or in other words, they can kind of just channel through it and flow without having to worry about resistance, but out of the scope of this video. So voltage, again, a difference between 2 points, difference in potential, which in actuality what that means is there's physically more electrons on this side than the other. So another example with like voltage without flow is inside of a, let's just say, magical tank, and there's electrons on this side, but there's more electrons on this side. These have a potential difference. So there's a potential difference between this side and this side. And these electrons want to reach equilibrium. And so there's a same amount on each side. And this creates a difference, which creates flow. So because there's this difference in voltage, you have a flow. Let's say we put a wire across them or something. You have a flow. These electrons are going to start channeling this way from this side to this side. And in a typical battery, this is how it is. So a lot of people think that the electrons flow from positive to negative. No, they flow backwards. Actually, they flow backwards to what's called like normal conventional sign convention. We kind of ignore that for a lot of things because it really doesn't matter. I'm going to be honest, but it is an important point to note that the electrons are flowing from the negative to the positive of the battery, not from positive to negative, because originally and historically we thought that the charges were positive flowing from positive to negative, so the normal sign convention stuck, but we later learned it was actually electrons flowing from negative to positive. But again, doesn't really matter for any devices. Don't go plugging your batteries in backwards. Doesn't really work. So now that we've gone through voltage, current, and resistance all in their own kind of like box, let's throw them together, shall we? So voltage is influenced by current and resistance they're both like multiplying together. So voltage is proportional to current and resistance. So as these increase, this is going to increase. As these decrease, this is going to decrease. So another way to look at this is you have a water tower, and you hold your voltage or your water at a constant level, and you have a valve at the bottom. The water coming out of this, let's say you're filling a bucket, the water coming out of here in like gallons per minute is your current. That's physically how much water is being moved through the pipe into your bucket. Gallons per minute is your current. Your resistance is how either the valve or the pipe is impeding the flow. So let's say we only have the valve 1/4 open. So 1/4 open, let's say 1/4 open. So 1/4 open would kind of equate to, let's say, 4 ohms of resistance. It's just 1/4, we flip it. So let's say we have the valve 1/4 open, 4 ohms, and we're getting out of here 4 gallons a minute. So our voltage, or in this case our pressure, of like our head pressure over here, your water pressure, your water pressure, V, or voltage, equals your gallons per minute, which is 4, by your resistance to your flow, which is, in our case, also 4. 16. So, great. Let's say we take and we open our valve more here. Open our valve to halfway open, which is 2 ohms of resistance, so less resistance here. But we still only get our 4 gallons out per minute. What is our voltage? So voltage equals gallons per minute, 4, or current, times resistance, or how much we're resisting the flow. We're resisting it less this time, 2, equals 8. So as we resist it less, but our amount of water coming out stays the same, we actually have to have a lower voltage value. Because if you think about it, like if you have a garden hose that's, like a normal garden hose is what, like half, 3/4 inch, maybe an inch, I'm not sure. If you have a garden hose pushing with like, a couple psi of pressure and you get, 5 gallons a minute or something, if you take and you double the size of that garden hose and you are pushing with that same pressure, you're going to get way more than like 4 or 5 gallons a minute. You're going to get like, I don't know, 8, 10 gallons a minute. You're going to get a lot more. So in order to still satisfy this gallons per minute, we have to have an effective lower pressure, which means our tank is down here. So that's kind of the key relation here. And if we can do the same thing over here, we can, let's say we have our 4 ohms back again. We've now made it, only a quarter open. We can solve for I now. If we know our pressure or our voltage is the value of 16 from earlier, we can say current, or amount of water we're going to get out, is equal to our pressure, voltage, divided by our resistance, or how open the valve is, and that is just equal to 4. So we have our amount. If we want to solve our amount per gallons per minute, it's just how much pressure do we have divided by how hard we are resisting it. So the harder we resist that, let's say we have the valve closed to almost completely closed, let's say 16, 1/16 open, we're only going to get 1 gallon a minute out of that. But if we put the valve wide open, completely open, to just 1, we're going to get a whopping 16 gallons a minute out of that bad boy. So this relation, current is proportional to voltage, but inverse proportional equal sign 1 over R. So we have that our current is proportional to our voltage, but inverse proportional to our resistance. So as resistance goes up, current goes down, but as voltage goes up, our current goes up now as well. And the same can be said for our, not same, but something similar can be said for our resistance. Resistance is proportional to our voltage, but resistance is inverse proportional to our current. And this was a little bit harder to wrap your head around. So resistance, the amount of like resistivity in the wire, is kind of a weird one, is by a product of the other two statements over there, proportional to voltage and inverse proportional to current. But resistance is usually an innate property of our wire or our conductor. So that's kind of a bad example to make out of it, but this is just a byproduct of the other two. So the system is constrained, or the system is functional. If we set this to some other value, in this 3 equation system, we would have a non-constrained system. It would break. The funny things would happen. Not good. So these two are more useful ones to solve real world problems. This is if you want to solve simply the resistance of something. But if the resistance is given like a known material, we don't really have to use this one very often, at least in like real world examples, like thinking like this. Obviously, we use all 3 of these all the time, but um, in basic, this one is hard to build intuition for because usually the resistance is just an intrinsic property, but it can be solved for based on how it interacts with the other two. Usually, you can think of this as how the resistance is interacting with the voltage and current, and based on these two, and we can solve for it here based on that interaction. And that's kind of my best way to think of it, because again, usually it is just an intrinsic property of things, and we can't usually change it in real world systems, like, or at least real engineering systems like power grids, power lines. We can't really just magically like, oh, we need that resistance a little lower. Doesn't really work. I mean, you can, but it gets expensive really fast. So this is more of a intrinsic property, and these two are things we can change. Usually, how power lines and power companies handle this is they crank this bad boy up and send it across the line so that the resistance actually is usually a little higher, or not higher. The resistance is usually the same. We crank the voltage up, but we decrease the amount of current. And that'll become important next video when we add power into this. So next we'll solve some, actually, we'll hold off on solving for next video because we still have to cover a couple basics of circuits and a few basic rules we have to follow and keep in mind always before we can start applying these to real circuits. So with that being said, I'll see you next time.